Okay, welcome back to our statistics lecture. And today we will have the last topic of our lecture, and this will be hypothesis testing. Because what we have done until now, we talked about the multiple linear regression last time, where we said, well, in general, we will not have only dependence between our variable which we want to measure. Let's say in our example, the variable which we want to explain the sales volume does not only depend, of course, on one variable, but it will depend on many variables. And this is, from the analytics, maybe a bit more complicated than the simple linear regression, but in the end, it is, of course, the same concept that we just put in our linear model all these other variables, but still, and this we have to admit, when we then calculate it, where do we have it? Here, our regression parameters and also our coefficient of determination. And this coefficient of determination, we could interpret that this would say from this correlation, we could explain 93% of our variable y with our three explaining variables visiting, marketing, and branches. That this is, of course, still only a descriptive explanation. So there is, of course, no causality. So we could not really say this variable is causes the variable x1 really causes with a specific probability the variable y. So it could be also the case that it is just the other way around, that y causes x1. And in order to give an answer to this question, what is the causality? For this, we will deal with the hypothesis testing. So we want to ask what kind of conclusions can we draw from our data to the total dependence to the whole population. So this is the case when you are just asking 1,000 people, maybe about the next poll in Germany, then you do not only want to know what is the opinion of these 1,000 people, but what you want to know is, can I draw from the answers of these 1,000 people some probability answer to the question, what will be the result of the next poll in Germany, so for the whole population, for everybody in Germany who can go to the poll. And In order to make a specific probability answer to these questions, we have to make some assumptions, especially about the distribution and the properties of our error terms. Remember, where did we have these error terms in our model? This was in this case that this is our theoretical assumption about some specific values of our beta parameters. But of course, our data, this is the data we have collected, that these data will not fit for 100% our model. Data we have collected will not fit by 100% our model. So we have some discrepancy, and this discrepancy is aggregated in our errors. So this discrepancy between the data and the model. And therefore, in order to make some probability answers, how good, so to speak, is our model, we have to make assumptions about the properties of the distribution of these error terms. And in my opinion, sometimes we forget about these assumptions when we are talking about results, and we say, well, this is significant, this is a significant variable or something like this. We will come to this in a minute. So we are at this stage here. So we assume that these error terms are distributed around 0, that they are all independent. This is really very, very important, that the variances, this is also very, very important, that the variances of every single error term is the same. This means homoscedasticity. And also independence means that the covariances of these error terms has to be 0 for all single pairs. This means we have no autocorrelation. And in the end, we make the assumption that these error terms are normally distributed normally distributed around the origin. And this assumption that this can be made, the argumentation comes from the central limit theorem. And if we make all these assumptions, then again, we look for good estimators, especially for unbiased estimators. And in the multilinear case, we have to calculate the estimator for the variance in a bit other way than we have done it in the simple regression, because we have to subtract from the number of the sample size now, so to speak, the number of our parameters. So if we have 4 betas, beta 0, beta 1, beta 2, and beta 3, then we have to subtract from the sample size. Maybe we asked 1,000 people. 1,000 people minus 4 is 996. And with this, we have to normalize the squared distances. And then we can show also that this estimator is an unbiased estimator for the variance we are looking for, and this is this variance here. We want to have an estimator for this variance of all single error terms. And with this estimator, then we go into our multiple model, and then we can show, and this comes from this linear system. Here we have y is x times beta plus epsilon, and then you see that how can we do it? I think I did it here on the next slide. No. Here we have it, that this is maybe the most important matrix which we have, because this determines in the end our parameters beta that we can show. That the standard error of our estimated beta values depends on the matrix V, especially the diagonal elements of the matrix V, and this is just these estimated general variance times these matrix X transpose times X and the inverse of this, and then we come to the standard error of our beta terms, and this means then we can show that the estimated parameters beta are also normally distributed around the true value of beta with the variances sigma hat squared times the diagonal elements of X. So this are the diagonal elements of X, Gx minus 1. Okay, and then we come now to the concrete hypothesis testing, because now, yeah, we want, so to speak, to test for our coefficient of determination, R square, and we want to test how good are our estimated parameters beta 1. And then in the beginning of the 20th century, there was shown that we have a variable f which is calculated via our coefficients of determinations like this. So it is r, so to speak, how much explains our linear model, the dependent variable y, normalized by the number of our of our parameters divided by 1 minus r squared. And here, this, you know, this was the normalization parameter, which we already know from our unbiased estimator here. You see, n minus k minus 1 we have also here. So these two numbers here is some kind of to normalize our value r squared with respect to the to our model, to our numbers of our model. And this parameter is then Fisher distributed, and this is just a specific distribution like the normal distribution, like exponential distribution, and so on. And in a minute I show how this distribution looks like. And then there was some guy, some Irish guy. He worked for an Irish brewery in the beginning of the 20th century. And because until this time, people more or less assumed that everything, or in the limit, they just calculated always with the distribution for these beta parameters, only the normal distribution. And this guy in this brewery, he showed that if you look exactly how this parameter is distributed, that this slightly deviates from the normal distribution, and this is then called afterwards the so-called student distribution, because this Irish guy, he published his paper under a pseudonym, and there he wrote that his name was student, and therefore the distribution is also called the student distribution. So, and now we come in concrete to our hypothesis testing. So what we are doing, we know that our F value is Fisher distributed. And now we make an hypothesis about our model. And if we take this F test, then we formulate the hypothesis that we start with the point that we think, well, I assume that there is no dependence or no correlation between y and our x variables. What does this mean? Let's look at our model. Our model was y is beta 0 plus beta 1, x1 plus beta 2, x2, and so on. What does it mean if we assume that there is no correlation between y and all our x values? Well, this then would mean that if we look at the data, that from our data we should find that every single beta value has to be 0. And this is written down here. And if we assume that every single beta value is 0, then we can conclude from this assumption that, of course, also the coefficient of determination has to be 0. Well, this is not very surprising, because R is the correlation coefficient, and if R is 0, then there is no correlation. Well, what is then the alternative? What does it mean if our assumption is not right? Well, our assumption that all betas are not right R0 is not right means that at least one beta value has to be deviate from 0, or in general that we find that R squared is also not 0. So in our model where we have branches, marketing and visits, we would assume that our number of visits does not have any impact on our sales volume, that our marketing budget does not have any impact on our sales volume, and the number of branches has no impact on our sales volume. And if we find then in the data that maybe the number of visits has an impact and the other two values do not have any impact, then our so-called null hypothesis is rejected. And now comes a very, very important part after formulating concrete hypotheses, and this is to find a reasonable significance value. So what we want to make is a probability answer to our question, is our null hypothesis right or not? And we want now to test, is our null hypothesis true with a probability of 1 minus alpha, and alpha is our significance level. And now, through the last 100 years, you will find that in general, doing statistics, we use significance levels of 10%, 5%, 1%, or 0.1%. And even sometimes, and this I had also in colloquia of bachelor thesis, many guys think that it is always right to choose a significance level of 5%. That you even do not have to talk about what is your significance level. Everybody should know that variable is significant, that this means that you have tested on a level of 5%. And there I have to say that you have to be really, really careful, because what is a good significance level, to answer these questions, this is always your task. When you look at some data, you have always to choose, when you pose a question, a good significance level. And also, we cannot say that there is some right significance level. We can also only say, well, in my question, I can argue that it is reasonable to test on a level of 10%, or it is reasonable that I test on a level of 1%. And yeah, even of course you can, so to speak, manipulate your analysis in choosing a specific significance level, because of course when you choose a very low significance level, then it could be the case that you do not reject your null hypothesis, although this hypothesis is not correct. So in this case, you of course have to be really careful. And then when we have chosen a significance level, Then we calculate from our data our f value. So from our data, we have calculated our r squared. We know how many parameters beta we have. We know what is our sample size, and then we can in concrete calculate our f value. And when we then have determined our f value using our chosen significance value, then we look at the distribution of our f value, and in our example here, let's see here. Here we have 3 variables. So in this case, we have k equals 3, and we have 1, 2, 3, 4, 5, 6, 7, 8 regions. So n equals 8, and where is our f? So this is in our example 3, 8 minus 3 minus 1 is 4. So we know then in our example that our f value is distributed f3, 4. And for this we have our distribution given in tables. So what we are doing here is we look at these tables here. F3, 1. Here we have our 3, 3, 4. Our 3. Here is our 4. So on a significance level of 90%, we have an f value theoretically of 5.34. And then we have to compare our empirical value, which we will calculate in a minute, and we have to look, is it larger or lower than our theoretical value f34. I should write here to a significance level of 10%. So, and then let's have a look. Our empirical value is, what did we had? I think 0.93. Here we have 0.93. This was r squared. And let's take our formula here, this one. So we have 0.93 over, what did we have in our example? K equals 3, and this divided by 1 minus 0.93 divided by 8 minus 3 minus 1. So let's do this. There we are. Here, hypothesis testing. Let's take an U1 here. This is our table. This was 0.93. And then let's calculate F 90 F empirical. This is then equals R squared over K equals 3 divided by 1 minus R squared, and this divided by 8 minus 3 minus 1, and I have to close 2 brackets. So we have an empirical value of 17.93. 17.93. And this means we are here in this region. Then Fm is larger than F theoretical, and this means we reject H0, and this means we have for alpha equals 10% a linear dependence between y and x vector. And now we have really this direction that our three variables x1, x2, x1, x2, and x3 really explains our variable y to a significance level of 10%. And nothing more is what we are doing in hypothesis testing. At first, we have to find our testing value. This is here our F value. Then we have to know how is this value distributed. These distributions sometimes look very complicated, but since we have a computer, we just can let the computer do all the calculations, and then we only have to compare our empirical value, which we deduce from our data, with the theoretical value. And if we are larger, then we can reject our null hypothesis. And usually you always formulate your null hypothesis in such a way that you in the end want to reject these null hypotheses. Okay, and now with the f-test, we have only in general tested. Is there in general a linear dependence between y and all our variables x1, x2, x3? But of course, we also want to know the dependence of every single variable. And this is done with the t-test. And this t-test is in the end formulated in a similar way as the f-test. But now our null hypothesis is not that every parameter is simultaneously zero, but we pose now the question, or the null hypothesis is now that we assume that a specific variable has no impact on our, in our example, on our sales volume. So we assume, for example, visits have no impact on sales volume. So for example, visits have no impact on our sales volume. And then, of course, the alternative hypothesis is that beta is unequal 0. So the alternative hypothesis is then, of course, the visits have an impact on sales volume. Well, in general, but we do not want to deal with this in this lecture. You also can formulate these alternative hypotheses also possible to formulate H0, H1 as beta I is larger or lower than 0, and this is so-called then a one-sided test, but we here in our lecture want only to test in two sides, and then we formulate the alternative that beta I is just unequal to 0. Again, we have to choose our reasonable significance level. We talked about this already in the f-test. Again, in general, very often we choose 10, 5, 1, and 0.5, 0.1% significance level. And then, in concrete, we again know that our t-value is t-distributed and that we have to calculate it in this way. And if we deal with two-sided tests, then of course beta m equals to 0. And thus, again, we have to calculate our theoretical t-value. And now be careful, since we have now a two-sided test, so we can deviate to the right and to the left with our value, then this means we have to look in the symmetrical t-distribution, not at the 90% level, but 95%, because if we take the symmetrical distribution, so this is the t-distribution, oops, this has to be t here, t-distribution, then this level here is 5% and these are 5%, so they both add up, adding up to our 10%. And then we know that our t-distribution also depends on this normalization number, sample size minus the number of parameters of our value of our model. And again, in our example, we have 8 minus 3 minus 1. So we have to look at the table of the t-distribution with n minus k minus 1 equals 4. And if we have a look there, then we find the value 2.13. And I show you the t-distribution. So what we have to look here is at 95% and at the value of 4. So we have here 2.13 as the theoretical value. So then we have 2.13 and we have to compare this with our empirical value. And let's start with empirical value of beta 1. How does it was defined? Let's also cut this. Oops. There we want to do. This is a bit too large. So this one. So then let's go to our data, beta m. Beta m we have calculated in our example. Where did we have it? Here. So for the visits we have 1.484, 0.71 and 9.001. So 1.484. Let's write it down here. This was beta 1 was 1.48. For beta 2 was 1.7, oops, 0.7. No. 0.7. 189,008. And beta 3 hat were 9008. And then of course we also need the standard errors. Of beta 1 hat, standard error of beta 2 hat, and standard error of beta 3 hat. And this you get also from your software package. It's not the right Excel. Where is it? Here. So that you see it. Here we have the standard errors. Oh, let's take all these values here. Well, let's take a new slide. So this one and this one here. So then we have T4, no, not T4, sorry, T amp of beta 0 hat is then 10.669 over the standard value is 7.579. So beta hat 0 over standard error of beta hat 0 and T amp of beta hat 1 is 1.484 over 0.99. T amp of beta hat 2 is 0.781 over 199, and in the end T amp of beta hat 3 is 9008 over 4150. And for this I also calculated this. We obtained these 4 here. Hopefully this is right. Let's have a look. Yes, just up. And this one. So 1.408, 1.63, 3.606, and 2.1717. What do we have to do with this? Well, we have to compare this with our value plus minus 2.13. So what we find then is we compare this in, oops, here we are, our distribution. Minus 2.13 plus 2.13. And what we find is that for these two, T of beta hat 0 is 1.48. T of beta hat 1 is 1.63, but roughly here, T of beta 2 hat is 3.606, and T of beta 3 hat is 2.717. So for beta 2 and beta 3, we reject H0. So marketing and branches are significant to a level of alpha equals 10%, and since for these two variables we are lower than the theoretical value 2.13, we cannot reject H0 for a level alpha equals 10%. So this means, and here you see the difference between the descriptive analysis and now our hypothesis testing analysis. From our descriptive analysis, we, so to speak, find that, let's choose here another color, we find beta 0 is roughly 10. So what does this would mean if you do not know the result from the hypothesis testing? How would you interpret that beta 0 is 10? Think of the dependence that y, our model is beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. If this model would be true, what would it mean economically? X1 is visits, X2 is marketing, and X3 is branches. What would it mean economically then when beta 0 is roughly 10? Why is sales volume? What could be an economic interpretation then of the parameter beta 0? Well, economically, you could interpret if all these numbers would be 0. So if I make no visits, if I invest €0 into the marketing and I have no store in the region, that then our sales volume would be €10. But this is only what I can deduce on a descriptive way. And now I look at the data that I have evaluated 8 regions. And what I find from my data is that to a level of 8%, although I find here a number different from 0, I cannot say that really to a level of 10% that this is a, so to speak, true value. So then I should be really careful to make the decision, well, I do not have to invest in marketing since I will obtain a sales volume of 10 anyway. And also for beta 1. And this is then really interesting for your decisions in your company that you see. Well, if I, for example, look at the data here, and more or less I can see if I make more visits, for example here for 16 and 13 I have sales volumes of 60 and 84, and if I have a very low number of visits I have only low sales volume. So just looking on a descriptive way I would say, okay, the more visits the higher is my sales volume. But if I make my hypothesis testing analysis, then the result is, well, although I get an impact that every additional visit will increase my sales volume by 1.5 euros, from a statistical interpretation, I have to reject that the number of visits have any impact on our sales volume for a significance level of 10%. And on the other side, I find that investing in marketing would be, so to speak, a good decision, because here I found from my analysis that the size of my marketing budget has a positive impact with for a significance level of 10%, and also if I have a store in the region or not has also a significant impact on my sales volume. And so from this analysis, and if I ask myself in the company, what should I do in the future times, then maybe I should shift my investment in the marketing budget and in opening new stores in the region and not to invest much more to increase the number of visits. Okay, so this we have done here already. Oh, we should do it also for significance level of 5% and also here for 5%. Then let's have a look and let's do this for a level of 5%. Then we have to do all in the same way, but we then have to look what is the theoretical value for a significance level of 5%. And for this, we go at first in the t-distribution. And there, hopefully, you can help me. With which number now I have to compare my empirical values. We are still in the same example that k is 3 and our data set, our sample size is 8. Can anybody help me? Any idea? If you look at this table. In the t-distribution, we have a two-sided test. So we have to double here. If we want to test to 10%, then we have to look at the 95% distribution. And if we want to test for a significance level of 5%, then of course we have to look at the t-distribution of 97.5%. So which number we have then to choose for the theoretical value? What is t of 8 minus 3 minus 1 for a level of 97.5%. You're still there? Yes, absolutely right. Then we have to choose this value. Well, and this value now we have to compare with our theoretical empirical values. These we had here. Oops. And let's go here. These were our z values. So then we have to compare Cmp with 2.77, and this is T4 of 97. 0.5%. So then answer the question, which parameters are now significant for alpha equals 5%. Oh, I have to round up, so this is 8. Well, in the end, you only have to look if these values are larger or lower than 2.78. So in my Excel table, I wrote here B. So this is beta 0, beta 1, beta 2, and beta 3. Well, C of beta 0 is of course again lower than 2.78. C of beta 1 is lower of 2.78. C of beta 2 is larger than 2.78, and T of beta 3 is now lower of 2.78, and then of course only beta 2 is significant to a level of 5%. So if you go then further in your analysis in your enterprise, and you still have restrictions, and you ask yourself, well, investing in a new store, this is really expensive. Maybe you don't have that much money, and then you have to choose between investing in a new store, this is beta 3, or increasing the marketing budget. And then from this analysis, you would say, well, I argued maybe that 10% is a good significance value level, but still I have restrictions because of my money balances. And then I would say, well, actually, I have to choose to invest in a new store or to increase the marketing budget. And then from our statistical analysis, we would say, well, then it would be better to choose the decision to increase the marketing level, because this is also significant for a lower level than 10%. Okay, and then also we need the F distribution, and here we have the table for 95%. So we should also test our model on a level of 95%. I gave you on the other slide the table for 90%. So which would be now the theoretical value of still, of course, 3, 4. And 95%. R6, where do you find this? Okay, then I have to admit that I have to say that you have to start to look downwards. So this is the first component. Or did I do it in the right way? Sorry. Right now I'm for myself not really sure. This is 3, 4, yeah. So and this is the second component. So it would be not 6.59, but you only have to interchange the 3 and the 4. And then the right one value, yes. So we have to choose 3 and 4, and then we are at 9.177. And if we take this number, oops, in here, F, 95% of 3, 4 is 9.117, and this is still, I think it was 17 or something like this, which R value that we had here, 1793. So still we have a general linear dependence to a level of alpha equals 5%. So, and in the end, please do not be shocked. I show you just how these distributions, the T distribution and the F distribution, look like, and what we see here, this is the so-called gamma function. This is defined via an integral. This is also a gamma function. So you see that these distributions are looking quite complicated. But what we also see is that the t distribution is approximately 4, and in general you say for n larger than 30 as approximately the normal distribution, and you see here that the F distribution is not symmetric, but what we also see here is if we take very large numbers, or if we take large numbers for n and m, then we also see that the shape of this not symmetric distribution also moves to the normal distribution. So what we see here also graphically is then the central limit theorem. Well, and then we are done with our content in this lecture. So let's stop.